So just remember that vectors have a magnitude and a direction. And so for velocity, velocity has a magnitude and a direction. So we can use a vector to describe velocity. The speed is the magnitude of that velocity vector. So the speed of an object is a scalar quantity since it can be completely described by number. However, the velocity of an object is a vector quantity since it needs to be described with a number and a direction. The speed of the object is the magnitude of the velocity vector. Okay, so first one, determine the velocity vector of a speedboat moving parallel to negative 512. So that's telling you its direction. Speed of 65 kilometers per hour. Okay, so we want to know what's the magnitude of this particular. If this had a magnitude of 65, then that is the velocity vector. Okay, but let's check it out. So the magnitude of negative 512 144 plus it, so that's 169, which is 13. Okay. So it's 13, we need it to be 65. So in this case, it's easy to see. If you think about that, that 5 times 13 is 65. So we need to multiply that vector negative 512 by 5. Right? Algebraically, if you want to show your work, you can go, okay, k times the magnitude. That's really the equation you're solving to get k. We just calculated, that was 13, right? So 13k equals 65, so k equals 5. Therefore, your velocity vector is 5 times negative 512, which is negative 2560. So when we have an object traveling in a straight line, we can come up with the equation of the line. What's nice about using vectors is that we can use the parameter as our time and start at time equals 0. Okay? And so basically not have it go backwards, although technically it can. It's not going to make sense for the application to have negative time, but it's kind of nice to use the vector form of a line rather than just a Cartesian form. So suppose an object initially at point A, so that's when time equals 0, moves with constant velocity v, vector b, and at time t the object is at r, right? So think about, there's your starting at A, getting to r after t seconds. There's your direction vector, that's parallel to AR. So you go up from the origin to get a point. Your original point at time 0 is A, and you travel along that line, okay? T times the direction vector B. So it's just a vector equation. So T greater than or equal to 0, right? For an application. And there it's summarized here. Okay, so here's an example. Object is initially at 510 and moves with velocity 3, -2. All right, determine the vector equation that describes the position of the object at time t in minutes. So R equals initial point 510 as a column vector plus t times 3, -2. In this case, t will be greater than or equal to 0. Okay, and a real number, I guess. Okay. So now substitute 3 in. That would be the position of the object at 3 minutes. Actually, you can do that in your head. 5 plus 9 is 14. 10 minus 6 is 4. So, okay, so the position vector is 14, 4. As a point, you show it in coordinate form, 14, 4. I would accept either one there for the same position. And then determine when the time when the object is due east of 0, 0. So there's 0, 0. Okay. You could actually do a little sketch here because it's in 2 dimensions. So your original point 5, 10. X is positive 3, y is negative 2. So kind of going down like that. I guess it starts at, in this case, we don't really want to have a negative t value, so it'll be there going this way. And we want to know the time when the object is due east, so that's the x-intercept, i.e. the x-intercept. Don't convert it back into Cartesian form and slope-intercept form. Think about it. You've got, if I write out my parametric equations, okay, then x-intercept is when y is 0. So I'm going to substitute 0 in to my y component. Okay, and time is going to be 5 minutes. Okay. You could then put it back in for x to get the location. That would be 20. It didn't say meters or not, so it didn't ask for that, but you could do that. So next one, vector equation, t greater than or equal to 0, describes the path where t is in seconds and distances are in meters. Initial position then. So if t is greater than or equal to 0, initial position is when t is 0, which means that goes away, and the initial position is 7, 5. Okay. And if that's a vector equation representing the path of an object, then the direction vector is your velocity vector. So calculate its magnitude to get the speed of the object. Works out nicely with that 10, and this would be meters per second. And then parametric equations, just x equals 7 plus 6t, y equals 5 minus 8, 2. Now we're given the parametric equations, put that back into a vector equation. For example 4. And if that equation is describing the path of an object, then your direction vector is your velocity vector. So the speed will be its magnitude. Just leave it as exact unless it asks to round. So a big hint in questions, if it says an object travels parallel to a vector, then likely that is not your velocity vector, okay? So in this case, it travels parallel to that and has a speed of 34. So we're wanting to find the vector equation of the path of the object, okay? We want t to be greater than or equal to 0, so we need to do a few things. Get the initial position of it, get the correct vector, velocity vector. So I'll start with the velocity vector. So let's remember, k times the magnitude of 815 has to give us 34. Okay, so that we can figure out what to multiply that vector by. So 8 squared plus 15 squared, and that actually is a perfect square. So k equals 2. So our velocity vector is going to be 2 times 8, 15, which is 16, 30. Okay, kind of have to work backwards a little bit. So this is a point that we get after 5 hours. So what we know right now is that we have a position vector plus t times that velocity vector. When t is 5, we get 60, 160. So we put 60, 160 in for r, and then I'm just going to call this x1, y1. Oops, and then put in, not t, put in 5 there for t. Okay. So now you want to solve for x1 and y1.
y again. So 60 equals x1 plus 80. 160 equals y1 plus 150. So your position vector will be negative 20, 10. Okay, so I need to finish off by writing out the vector equation. Question?
Could you also do our start at 6160 and then add 3 hours to it and get time off position?
Oh, for part B?
Yeah.
Yeah.
And like I guess there's another question later on once we find the initial position.
Yes. But technically, for the vector equation, if you're using t greater than or equal to 0, we did have to do this for part A.
Okay.
But if all you're asked for part B, then you don't have to.
But because I have, I'm going to use it.
Yeah, if all you're asked, given that information, was the object after 8 hours, that's just going 3 more hours than what you already had from this point. So you could use that. But we were asked to determine the vector equation of the path of the object overall, sort of the general case. So t has to be greater than or equal to 0, so you need to show that.
So what's that? 80, 128 minus 20 is 108. And 40.
Okay, so now, determine when the object will be due south. So we're changing this to due north because it doesn't work for due south. Okay, so you think about doing a little diagram. Remember the equation. So original initial point negative 20, 10, and then 60 for x, 30 for y, so it's going in this direction. So we're wanting to know where it's north of 0, 0, and so this is going to be the y-intercept. So we want the y-intercept, which means when x equals 0. So from our parametric equations, we'll have 0 equals negative 20 plus 16t, and then solve that. And that's going to be 5 over 4. Doesn't say what point, but it says what's t, what's the time when it does reach that. And to the nearest tenth of an hour, we're also going to change that to the nearest hundredth. Come on, lots of dots there. 1.25 hours. All right, so that's how long it takes to be due north of 0, 0. We're done.